Students, in this video I am going to discuss model 2, which is MM1, that means Poisson arrival, Poisson departure and single server. And then N is the capacity of the system. That means only N number of customers they are allowed in the system. And then first come first serve. This is the discipline. Fine. So now here queuing model with Poisson arrival, Poisson departure, single server, capacity of the system is equal to N customers and service discipline is first come first serve. So this is the model. Fine. So here first understand the model. So this is the description queuing process. Initially we have assumed that initially here there are 0 number of customers, then 1 number of customers, 2 customers, n minus 1, and then finally n. Fine. After n number of customers, there will be no customers allowed to enter the system. Finally, fine. So system is closed after n number of customers because capacity is exactly equal to n. So here we have assumed that lambda n arrival rate is constant value lambda when n is less than n, where n is 0 to n minus 1, because when n minus 1, then you may permit one customer, so that total number of customers will be now n. After this you may not allow anyone, so otherwise the capacity, this n will be violated. Fine. So here only n number of customers are allowed, so that's why you may allow the customers up to n minus 1. That's why here is less than n, and when for n greater than equals to n, arrival rate is 0. Now mu n is mu, departure rate is mu. There is no restriction because after this you are not taking any other state. That's why there is no need to restrict yourself on mu, because you are restricting yourself up to n number of customers, up to nth state. So obviously you are considering departure rate as mu. Now from general Poisson queuing model, we have this equation. This is the general equation for n is equal to 0, 1, 2. We have already derived this, and total summation of probabilities is 1. Here we have assumed that lambda naught, lambda 1 up to lambda n minus 1 is equals to lambda, and mu 1, mu 2, mu n is mu. Fine. So now here if you will take this, so you can take n as 0, 1, 2, n. Fine. So now Pn is rho raised to the power n p naught. This is from the general formula which we have already derived for Pn, and for n greater than n number of customers, probability will be 0. So you can allow up to Pn only. This is the nth state, Pn. So P capital N. Fine. So this is the probability. Now solution of, so this is the step 1. So you have derived the equations. Now find out the values of P0 and P1. So solution of the steady state equations, summation of n from 0 to infinite, Pn is equal to 1 and Pn is equal to rho raised to the power n, P0 is n less than equal to n. So here is less than equal to n because we are considered up to nth state, Pn capital N. Fine. That's why equality. So and there will be no state after n, so that's why 0 when n is greater than n. Fine. So now substitute all these values. So P0, P1, P2, P3, Pn is equal to 1, because after n probability will be 0. But P1 is evaluated with the help of this, P2 is evaluated with the help of Pn. So ultimately we are getting this equation. P0, you can take P0 common. So 1 plus rho square plus rho raised to the power n will be 1. This is a geometric progression or geometric series with finite number of terms. So here there are two cases. either rho, that means traffic intensity. Rho means lambda by mu. If this is not equal to 1, then we are having this sum. And if we are having this sum for finite number of terms, then from here P naught is 1 minus rho divided by 1 minus rho raised to the power n plus 1. Second, when rho is exactly 1, then you can put here 1, 1, 1, 1. How many times? N plus 1 times. Because you are included 0. 0 plus 1 plus 2 plus 2 n. So this will be total n plus 1 terms. So P naught into n plus 1 is equal to 1. So P naught is 1 upon n plus 1. Or you can directly evaluate this from here. Just apply L'Hospital rule. So when you substitute rho is equal to 1, you will get 0 by 0 form. So just substitute rho tending to 1 and apply L'Hospital. Again you can find out this. Again you can evaluate this. Fine. So you may use any one of the them, any one of the technique. Let's see. So this is your P naught. P naught is from here when rho is not equal to 1, and when rho is equal to 1 we are having P naught is equal to this. P naught is equal to this. So this is written here. Fine. So now put this P naught here, put P naught here. So we get Pn is equals to Pn, because Pn is this for n is less than equal to n. Now since we are having two cases, one for rho not equals to 1 and another one is for rho equals to 1, so that's why Pn is two types. One is this 1 minus rho upon this multiply by this rho raised to the power n. So this is this when rho is not equals to 1, and when rho is equal to 1, so just take this rho raised to the power n, multiply by P naught, and for this P naught is 1 upon n plus 1. So this is substituted here, but rho is 1 here, so this is equal to 1 upon n plus 1. Fine. And n is here 0, 1 to n. So now step number 3, find the indices, expected number of customers in the system, which is ELS, and this is equals to summation n from 0 to capital N NPN, because we have allowed up to n number of customers. Now substitute the value. So here first we are considering this for rho not equals to 1. Fine. So this is for rho not equals to 1. So we are substituting this value. So substitute this value here. Again you can take rho here from here. So we are getting 1 minus rho 1 minus rho raised to the power n minus 1 n plus 1 summation 0 to n rho raised to the power n minus 1. This can be rewritten as 1 minus rho by rho divided by 1 minus rho raised to the power n plus 1 summation n from 0 to n, and this can be rewritten as d by d rho raised to the power n. Fine. Now you can take derivative term outside and summation inside, so we get this term. You just take derivative outside and summation inside. So this is the series, geometric series with finite number of terms, which is nothing but 1 minus rho raised to the power n plus 1 divided by 1 minus rho. Fine. So if you are not able to find out this, so there is an way. Here is, suppose s is 1 plus rho square plus rho raised to the power n. This is sum. Just multiply by rho s will be rho plus rho square plus rho cube plus rho raised to the power n plus 1. Now subtract. So 1 minus rho s is equals to subtract. So what we will get, they will be cancelled out. So only the first and last term will be left. 1 minus rho raised to the power n plus 1. So from here, this is s. So s will be 1 minus rho raised to the power n plus 1 divided by 1 minus rho. So this is the proof of this formula. Fine. So this is the proof. So this sum means this sum, and this is evaluated here. Fine. So now differentiate this. So what we will get this expression. Finally, after solution, we get this. For rho not equals to 1. When rho is exactly 1, then we will use the second formula, 1 upon 1 plus n plus 1. So substitute Pn is equal to here So we get npn, but pn is nothing but 1 upon n plus 1. So 0 when n is 0, then 1, so 1 p1, that means 1 upon n plus 1, plus 2 p2, that means this is equal to 0 p naught plus p1 plus 2 p2 plus n pn. Fine. So now 0 p naught is 0, p1 is from here is 1 upon n plus 1 plus 2 p2, so 2 upon p2 is from here 1 upon n plus 1, and so on. So finally we get this 1 plus 2 plus n upon n plus 1. Sum is n into n plus 1 divided by 2 divided by n plus 1. N plus 1 is cancelled out with this. So ultimately n by 2. So this is the sum. So fine. So ELS is either this or this depending upon row. So here we have this. ELS is this value when row is not equal to 1, and when row is equal to 1, n by 2. Now with the help of Little's formula, EWS is ELS by lambda. So just divide by lambda here. So when you divide by lambda and put rho is equals to lambda by mu, so we get this one for lambda not equals to 1, and this is n by 2 lambda when rho is 1. Fine. Similarly EWQ is this EWS minus 1 by mu. So this is EWS, this value for rho not equals to 1 minus 1 by mu, and after doing the calculation we get this. Similarly this n by 2 lambda minus 1 by mu is rho equal to 1. And finally ELQ means here is the waiting time in the system, waiting time by the Q. This is the ELQ is lambda EWQ. Fine. So is expected length in the queue. This is the expected length in the queue. So this is lambda EWQ, but EWQ is this. So just multiply this by lambda. So we get this for rho not equals to 1, and n just multiply by lambda. So n by 2 minus lambda by mu, but lambda by 2 is rho, and here rho is 1. So that's why n by 2 minus 1. Fine. So this will be 1. So this is all indices for this model. Let us take a simple example. If for a period of 2 hours in the day, 8 to 10 hour, day means 8 to 10 am, trains arrive at the yard every 20 minutes, but the service time continues to remain 36 minutes. That means between two trains, fine, the time is 20 minutes and the service time is 36 minutes. The calculation for this period, the probability that yard is empty. Find out the probability that the yard is empty. Average queue length on the assumption that the line capacity of the yard is limited to 4 trains only. So this is the we have to find out. So first, what is given to you? Lambda is 1 by 20 trains, because the duration between two trains is 20 minutes. So rate will be 1 by 20 trains per minute. Mu is service rate. Each train requires 36 minutes for service. So servicing rate will be 1 by 36 trains per minute. Capacity you have already seen, 4 trains only. So n is 4. So what is rho? Rho is lambda by mu, 36 by 20, 9 by 5, that means 1 by 0.8, which is greater than 1. So which is greater than 1, that means we have used this formula. Rho is not equals to 1, rho is not equals to 1. Similarly here rho is not equals to 1. So that means rho is not equals to 1. So we will use the formula for rho is not equals to 1. Now here what is P naught? The probability that the yard is empty. Empty means 0 train. Probability that the yard is empty. So this is P naught. And according to the formula, P naught is, we have evaluated as this. P naught is, this is for P naught when rho is not equals to 1. So 1 minus rho upon 1 minus rho raised to the power n plus 1. So substitute it here. 1 minus rho upon 1 minus rho raised to the power n plus 1. So 1 minus 1.8 divided by 1 minus 1.8 raised to the power 5. After simplification we get this. So this is the probability that yard is empty. Find now the average queue length. Average queue length on the assumption that the line. So average queue length of the system, actually. System is ELS. And ELS is nothing but this for rho not equals to 1. So this is ELS. So, or this formula is evaluated with the help of this NPN. This is the basic formula. So either you can use this, or directly if suppose you have forget the formula, then you can use the basic formula. So this is the basic formula, 0 to 4, which is nothing but 0 plus P1 plus 2P2 plus 3P3 plus 4P4. Fine. So rho P naught, P1 is nothing but rho P naught, 2P rho square, that means this value, 3P3 means this. So after solving this we get 2.7 trains, or I directly you can substitute the values here. If suppose you forget the formula, then you can use the basic formula. तो अगर आप भूल भी जाए तो बेसिक फार्मूला याद रखें, यहाँ भी आप पुट कर सकते हो. फाइन. तो सब्सटीट्यूट द वैल्यूज एंड फाइनली 2.7 ट्रेन्स, यानी कि 2.7 ट्रेन्स आपके यार्ड में रहेंगी ऑन एन एवरेज. फाइन. सो दिस इज द मॉडल. Now in the next video we will discuss the third model. Fine. So thank you.